Hello. Hello.
Good morning, everyone. I welcome you in this. Good morning, everyone. I welcome you in this another session of control system. In the last lecture, we have seen about the steady state error, that what are the steady state error and how to derive these. Today, we are going to take an example on this. The problem has been defined in front of you that you have to find out the steady state error for a transfer function 5 upon s square plus 7s plus 10, and the input provided to this system is step. It is unit step. So the solution is from the problem statement. We know that the step input is 1 upon rs, 1 upon s. When we substitute this into the error signal, we will be getting that es will be equal to s square plus 7s plus 5 upon s into s square. S into s square plus 7s. So when we substitute this es into this, we will be getting that since ts is stable and subsequently es does not have any right half plane poles that or j omega poles other than at the origin, we can apply the final value theorem that when you substitute t tends to infinity, we will be getting that es is equal to 1 by 2. The steady state error in the terms of GS, if you would like to write, then we can write it in such a way that ES is equal to RS minus CS, and we know that the output is equal to the multiplication of, it's not just a simple multiplication, but eventually, if we go with the frequency domain analysis, it is a convolution of the GS and ES. So therefore, your ES will be equal to RS upon 1 plus GS. So we now apply the final value theorem. That is when the t tends to infinity, then in this case the limit s tends to 0, which is equal to s into rs upon 1 plus gs. Now there are few of the test signals that we implement on the system to identify, to check the performance of the system. These are the standardized test signals, that is the step, ramp and parabola. So let us take each input and evaluate its effect on the steady state error by using the equation e infinity limit s tends to 0 s rs plus 1 plus ds. Now it has to be remembered that thing that in the s domain, if the s tends to 0, then in time domain the t tends to infinity. So here basically your t tends to infinity defines your s tends to 0. That is, your s is tending towards a 0 when we are having infinity over here. Now, when we apply the step input in this equation, we will be getting that Rs is equal to 1 upon S. Then we can find it out that E infinity or E step infinity will be equal to 1 upon 1 plus limit S tends to 0 GS. Now, similarly, we can implement it for the ramp input as well. And in this case, nothing will be changed, but except your one x extra term of S will be added over here. That is equal to 1 upon limit of S tends S plus GS. We can write this as a Kp and this can be written as a Kb. Later on, we will see it in the upcoming slides.
The current level increases all of a sudden, whereas the voltage reduces because the fault is what? A low voltage phenomenon. So to determine the magnitude of fault current throughout the power system after the fault occurs. So it is very essential to identify the fault currents when the fault occurs, because it has been approximated that around the fault current rises towards 20% or 2 to 3 times more than the rated current. So it is very essential to meet out the equipment's requirement or the equipment coordinations which are connected in the power system network to meet out the faults current during the mal operations or during the abnormal. or during the, we call it contingencies. Now to select the ratings of the fuses, circuit breakers and switchgears, we require the amount of or the level of the fault current which has been reached to its peak value, so that the equipments like the fuses, circuit breakers or the switching ratings must be kept higher than these fault current ratings or the fault ratings, short circuit ratings. So to check the short circuit ratings or the MVA ratings of the existing circuit breakers when a new generators are added into the system as well. So basically, we require to do the short circuit analysis or the fault analysis to identify the MVA ratings or the short circuit ratings of the various equipments which are going to be connected into the power system networks in reality. Now, what is a balanced three-phase fault? When all the three phases are short circuited to each other and to earth. That means we are having the three-phase system, and when all the three phases are getting short circuited with the earth, such type of fault is also called as triple LG fault. So such type of fault creates a balanced fault where all the current and voltages levels changes simultaneously. It is not only required that only the single phase or a two phases will be changing its value. It's changing its fault current and voltage levels. No, when all the phases simultaneously changes its fault current and voltage levels, such type of balance system is called as balanced three. Such type of fault is called as balanced three-phase faults. That means the voltages and currents of the system balanced after the symmetrical fault occurred. So it is enough to consider on any one phase for the analysis. Now, what is the short circuit capacity? The short circuit capacity, it is the product of the magnitudes of the pre-fault voltage and the post-fault current. We know that the fault is a low voltage phenomena, and the current is in the post-fault conditions. The current is very high, is comparative to higher than the rated currents of the system. Therefore, it is essential to consider the pre-fault voltage and the post-fault current to getting the maximum short circuit capacity of the system. It is used to determine the dimension of a bus bar and the interrupting capacity of a capacitor. Now look at this. Let triple SCC is the short circuit capacity, which is equal to the pre-fault voltage V0 and the post-fault current, that is your IF. We use a fault current, not the phase currents. Okay, it is important to distinguish the fault current and the phase current. The fault current is quite different with the phase current. The reason is that if you are having a fault only in the single phase, then in that case a phase current will be different from the fault current of the other phases. Okay, for an example, the fault occur at the phase A, then the phase current of the IB and IC will be different than the fault current in the phase A. Is this clear? That's why it is important to keep the distinctions, to keep the fault current, to denote the fault current by IF. Now, what is IF? IF is a fault current which flows through the short circuit path of the network. Okay, where mathematically it is defined by Vt upon Zt, where Vt is the terminal voltage at the location of the fault, and Zt is your fault or the terminal impedance, fault impedance or the terminal impedance. Therefore, we can write for a single phase the short circuit capacity can be written as Vt square upon Zt, which is equal to SB single phase upon Zt per unit MVA per phase. It is the MVA per phase. That is the short circuit capacity per phase. Okay, and if you would like to calculate for a three-phase, complete three-phase, we can calculate it by short circuit three-phase base value, base capacity, that is the base power, three-phase base power upon the ZT per unit in MVA. Okay. Similarly, with the help of this short circuit capacity, we can directly calculate the fault current. Usually, the short circuit capacity is being defined by the manufacturer. Okay, and by the help of that short circuit capacity, we can identify the fault current. Therefore, the fault current would be the three-phase short circuit capacity in MVA upon root 3 into VLB, that is a line voltage, base line voltage of the base at the base value. That is line voltage at the base value. Okay. In this way, we can easily calculate. We can easily calculate the short circuit capacity for the two phase, for the single phase as well as for the three phase system. Okay. Another thing, it's the procedure for calculating the short circuit capacity and the fault current. Now we have understand the what is the short circuit capacity and what is the fault current. Now how to calculate the short circuit capacity and the fault current? What is the procedure and how we can effectively and accurately attain it? Therefore, the very first method is to draw a single line diagram and select the common base SB, MVA and the kilovolts. That means we have, suppose for an example, we are having a power system network. We have to first of all draw the single line diagram of the network and or the network in which the fault has occurred, and then we select a common base and base power and base voltages for it. The base voltage, this base power will be selected on MVA base. For an example, 100 MVA or whatever is the base arbitrary value which you would like to choose. And similarly, the base kV or the base voltage has to be selected. After this, we have to draw the reactance diagram and calculate the total per unit impedance from the fault point to the source. That is the Thevenin's impedance ZT. We have to draw the reactance diagram and we have to calculate the total per unit impedance from the fault point to the source. In this, we generally apply the Thevenin's theorem to calculate the terminal voltage and the Thevenin's impedance at ZT. That is, we will calculate the VT and ZT using the Thevenin's theorem in this. After this, the next step is to determine the short circuit capacity and the fault current for the given reactance diagram for the given power system network, of which we have drawn the single line diagram and the reactance diagram for the same. I hope this is clear to you now, that these three steps have to be followed up to calculate the short circuit capacity and fault currents. Now let's discuss about the algorithms using the bus impedance matrix. I've told you that we will not be using the admittance matrix in calculation of the fault analysis, but perhaps we will be using the bus impedance matrix for the fault analysis. Now, what is the algorithm for it? Just consider
Now the algorithm states that consider a n bus network and assume that three-phase fault is applied at the bus K through a fault impedance of ZF. Now, the pre-fault voltages at all the buses will be defined by this bus matrix, voltage bus matrix, that is equal to V bus 0 is equal to V1 0, V2 0, so on till Vk 0 and Vn 0, where kth is that bus at which the three-phase fault has occurred. Now, we will be drawing the Thevenin's equivalent circuit, that is a zeroing of all the voltage sources and add the voltage source at Vk0 at the faulted bus K and draw the reactance diagram. This is the beauty of this Thevenin's equivalent circuit, that it ease the calculation by making all the other voltages equal to 0, because it will make the system quite easier to solve. At the bus Vk naught is the bus K where the fault has occurred, and now let's draw the reactance diagram for it. Now the change in the bus voltage due to the fault will be given by this volt value, that is the delta V bus is equal to delta V1 and so on till delta Vk and so on till delta Vn. If we are having the n buses and k is the faulted bus, the bus voltage during the fault is V bus is equal to V bus naught plus delta V bus, and the current entering into all the buses is 0, and the current entering into the faulted K bus is negative of the current leaving the bus K. Therefore, your deviation in the difference in the voltage bus will be equal to Z bus into I bus, where Z bus is your impedance matrix bus of the bus. That is Z11, Z1K, Z1N, ZK1, ZKK, ZKN, ZN1, ZNK, and ZNN. If you are having the n bus matrix, if you are having an n number of buses, then the Z bus will be of n cross n, and Z11, ZKK, ZNN are your self impedances, and Z1K, Z1N, ZK1, ZKN, ZN1 and ZNK are your off diagonal elements, are also called as mutual impedances. So when we substitute these values, we will be finding out the fault current will be 0 for all the other value, for all the other buses except for the bus number K, because the fault has occurred only at bus number K. So the current will be existing only at the bus K. The fault current for all the other buses except the bus K will be 0. So when we substitute these values, we will be able to calculate the fault voltage at bus K. That is Vkf is equal to Vk naught, that is your pre-fault voltage at the bus number K, minus the fault or the voltage drop due to the current, fault current, that is been defined by the ZKK into IKF. IKF your fault current. Therefore, the fault voltage will be equal to ZF into IK, and the fault current will be equal to P fault voltage upon the sum of the ZKK plus your ZF. Okay, the self impedance of the bus number K plus the fault impedance. Therefore, by this method, it is very easy to calculate the fault current and the fault voltages. Now, once we have the knowledge of this fault current and fault voltage, it will become very easy for the operator to identify the short circuit capacity or the ratings of the equipments need to be connected in the system. Now, let's discuss about the fault analysis for an unbalanced faults. Till now, we have discussed for the balanced faults. Now, it is very essential to know the concepts for understanding the unbalanced faults. Now, in the previous section, just right now, we have discussed that what are the balanced faults. I told you that the balanced faults are those faults in which the fault voltages and the currents changes simultaneously or symmetrically throughout all the phases when the fault occurs. Whereas in the unbalanced faults, the fault voltages and currents will not change symmetrically. They will change unsymmetrically. That means the fault voltage will be different in case of for the other two phases, and the fault current will be existing only for a particular phase on which the fault has occurred. If it is a single phase fault, it will be only for a particular one phase, either out of A, B, and C. If it is a line to line fault, two double line faults, then it may be a fault current for the consecutive fault currents for the phase A or phase B or any of the other two phases on which the fault have occurred. It is not always mandatory that the fault will only occur at the phase A. No, it for a combination for the analysis purpose we consider it on the phase A. We can also consider it for the phase B or C. It is not always necessary to understand. Okay, now let's move further. So what are the unsymmetrical faults? The unsymmetrical faults are those faults in which one or two phases are involved, that the fault occurs on single phase or on the combination of the two phases. Also, unsymmetrical faults are those in which the voltages and currents become unbalanced and each phase is to be treated individually. We cannot consider it for a single phase. Like in a three-phase fault or in a balanced fault, we can consider a single phase circuit for the analysis of all the three phases, for analysis of the complete network. But it is not. We cannot do this in the similar manner in this way for unbalanced faults. Now, the asymmetrical faults are those types of faults in which we have categorized into those two categories. First is the shunt type faults and the series type faults. Now, what are the shunt type faults? Shunt type faults are when there is a connection or a short circuit between the phase and the ground, or a phase between the phase. Such type of faults are called as shunt type of faults, like line to line fault, line to ground fault, or line to ground fault. That is also called as a double line fault. Whereas the another category for the unsymmetrical fault is of series type of faults. The very good example is the open conductor faults. That means one of the conductor or the two conductors got break and there is a discontinuity of the power. Okay, that is an open conductor fault. Sometimes you have seen that your distribution lines get damaged due to the falling of the trees and the complete conductor is fell down on the ground. Okay, that is the conductor has got breakdown from between. That is one type of open conductor fault. Now, let's discuss about some of the fundamentals of symmetrical components. Symmetrical components can be used to transform three-phase unbalanced voltages and currents to balanced voltages and currents. That means we are having a balanced system and due to some conditions it becomes unbalanced. Now, to do the analysis, it is always preferred to do the analysis on a balanced system. We cannot, it will be very complex and tedious task to do the analysis on the unbalanced system. Now, how to do this? How to solve this problem? It will be very easy for us if we transform that unbalanced voltages or currents into a balanced voltages or current. And the method used for this is been used as a symmetrical components. Now the three-phase unbalanced phasors can be resolved into the following three sequences: the positive sequence components, the negative sequence components, and zero sequence components. That means we have resolved the three unbalanced phasors into the three sequences. Sequences of what? Positive sequence, negative sequence, and zero sequence. And the components associated with it are termed as positive sequence component, negative sequence component, and the zero sequence component. Now, what are the positive sequence components? Let's discuss them. The positive sequence components these are the three phasors with equal magnitudes, which are equally displaced from one another by 120 degree, and the phase sequence is same as that of the original phasor. If we are having the sequence of original phasors as A, B, C, then these positive sequence components will also follow the same phase sequence A, B, C. And the most important thing is that their magnitudes are equal. The magnitudes of all the phasors of the positive sequence components are equal, and they are equally displaced from one another by 120 degrees. The next sequence component is a negative sequence component. The negative sequence components are those three phasors with equal magnitudes and also equally displaced from one another by 120 degrees. And the phase sequence is opposite to that of the original phasors. That is, the original phasor is A, B, C. Then the original phasor, then in this case it will be A2, B2, and C2. They are defined by A2, B2, and C2. For an example, if the original phasor is anti-clockwise, then the negative sequence components will be clockwise. And if we move from the negative anti-clockwise, then it will be ACB. The next sequence component is the zero sequence component. The zero sequence component is the one in which all the magnitudes are equal. All the three phasor magnitudes are equal, and they are displaced from one another by a 0 degree. There is no angle between the displacement. There is no displaced angle between each of the phasor of the zero sequence component. They all are in the same phase. Okay, and they have been defined by A0, B0, and C0. That means if I'm writing for the voltage phasor, then it will be VA0, VB0, and VC0. Where VA0 is the positive zero sequence component for phase A, VB0 is the zero sequence component for phase B, and VC0 is the zero sequence component for phase C. Similarly, we can say for the negative and positive sequence components. For an example, if I am writing at a VA2, that is VA2 is the negative sequence component for phase A, VB2 is the negative phase sequence for phase B, and VC2 is the negative phase sequence component for phase C. Similarly, VA1 will be the negative positive phase sequence for phase A, VB1 will be the equal to positive phase sequence for phase B, and VC1 will be equal to the positive phase sequence for phase C. So that was the introduction for the basics. Now let's talk about the relationship between the symmetrical components, and the balanced vectors. Now, I've told you we are having the three phases, and we are talking about the voltages first of all. Let's the similar fashion we can apply for the current also, but let's discuss with the simple conditions of the voltages. The very phase voltages are being defined as VA, VB, and VC, and we assume that VA, VB, VC are an unbalanced system. They are not balanced. That means their voltages, the magnitudes of the phasors, three phases are not equal. Neither they may have they have the phase angle of 120 degree. It is not defined. They may be having the different phase angles. Okay. Therefore, I have just for an example consider the phase A voltage. The phase A phasor voltage VA have been divided into three components, that is the positive, zero, positive, and negative. That is, look at here. Look at this. This have been defined. Look at this VA. This VA have been defined into the three components, that is a VA0, VA1, and VA2. Similarly, the VB is been defined into VB0, VC0, VB1, and VB2. That means the zero, positive, and negative sequence component. Similarly, the VC is been defined as VC0, VC1, and VC2. I hope this is clear to you. Now, I've done nothing, but I've written them into the matrix form. I've written them into the matrix form where VA, VB, and VC are their unbalanced phasors, and VA0, VB, VA1, and VA0 are your balanced phase components, symmetrical components. Now, what is this A? A matrix. That is your matrix with a component of alpha. This alpha component is called as the balancing factor. It is also called, sometimes called as a balancing factors. That is the relationship which is established between the various components of the positive, zero, and negative sequence components for a particular phase, which makes them balanced. Okay. Here where alpha is nothing, is having a value of magnitude of 1 and angle of 120 degree. Angle of 120 degree. So in this way, if I write this alpha matrix in this fashion, I will be able to create a matrix. Which makes the system balanced. Similarly, we can obtain for currents also. Similarly, we can obtain the values for the currents also. Now, let's talk about the sequence impedances. Now, these are the sequence impedances, are the impedances offered by the power system components to positive, negative, and zero sequence currents. That means if in a network, in a positive sequence circuit, the positive sequence current will be flowing, and the impedance offered by that positive sequence current will be called as a positive sequence impedance. Okay. Similarly, it is common for all the other two components also. That is the negative sequence component and the zero sequence components. So if we talk about the positive sequence impedance, it is the impedance of a component, and the positive sequence currents alone are flowing, and this happens only in the positive sequence circuit. Negative sequence impedance are the impedances of the component when the negative sequence currents are alone flowing in the network, and zero sequence impedance are the components when the zero sequence currents are alone flowing into the network. Look at this. This is a sequence network for a generator. For an example, look at this pause circuit first. We are having one positive sequence voltage VA1. We are having the in this VA1, the positive sequence current is only flowing into this. We do not have any other current component in this. Only the positive sequence current component is flowing into this circuit. So we can say that the positive sequence, this is your this impedance Z1 is your positive sequence impedance. And when the positive sequence impedance and the other components are being connected with the flow of positive sequence current, that network is called as a positive sequence network. Is called as a positive sequence network. Similarly, look at this network. In this network, only the negative sequence current component is flowing to the circuit, and no other value, no other component is flowing. And the impedance offered due to the negative sequence current component is Z2. And that's why when we interconnect these networks and components only with reference to the negative sequence, that network is called as a negative sequence network. Similarly is for the zero sequence network. Okay. Now look at this. This is an example for the sequence network for a generator. It is very essential to understand that in the positive sequence network, only this network for a generator will be consisting the generated EMF component for phase A. That means we are only defining for the phase A. We will be only I've told you in the previous section also that we can do the analysis for a per phase basis only when the system is balanced. Now, with the use of these symmetrical components, we have made the system balanced. We have made the unbalanced system into a balanced system. Now, that's why we can do the per phase analysis now. That's why we can do the per phase analysis. That's why we have created only the per phase sequence circuit for phase A. And in this case, only the per phase sequence circuit for the positive sequence network will be consisting the EMF generated by the generated by the phase A component. This is clear. That's why it is written over EA. I think this is clear now. Now, similarly, for the sequence network for the generator, for the negative sequence in the zero sequence networks, the generated EMF will not be considered. Only the negative components, impedances and voltages and currents will be included in the network for the negative and zero sequence network. Okay, we will not include the generated EMF or the induced EMF. It is also called as the induced EMF in the negative sequence networks and the zero sequence networks. That means this will be considered only in this one and will not be considered in these two sections. I hope this is clear. Mark it in a star. This is very important to keep the concept. Put as a 3 star in this. Okay. Mark 3 stars in this section because it is very important to keep in mind, because otherwise the students, what does they make the mistake that they include the induced EMF again and again in all the network sequence, in all the sequence network. No, it will only be considered only the positive sequence network in case of generators or either in the motors. Okay, either in the generators or in the motors. We will consider the induced EMF only in case of positive sequence networks. Okay. Look at this. This is a sequence network for a transmission line. This is a sequence network for a Transmission line. We do not have any induced EMFs in the transmission lines. Okay, that's why the positive sequence network, negative sequence network, and zero sequence network will not contain any of the induced EMF component. Only the impedances associated with the positive, negative, and zero sequence components will be included into the network. Okay, that means if I write the Z1, Z2, and Z0 are your positive, negative, and zero sequence impedances calculated from the Thevenin's network. Okay, is the one. It is a Z1, Z2, Z2. VA1, VA2, and VA0 are your positive, negative, and zero sequence voltages. IA1, IA2, IA0 are your positive, negative, and zero sequence currents for phase A. For phase A. Similarly, we can identify if we have the knowledge of phase A components, if we have the knowledge of all the phase components for a positive phase sequence component for a phase A, we will be very easy. It will be very easy for us to calculate for the other two phases, for the phase B and phase C, just by using the alpha operator. Because what does the alpha operator does? It rotates the reference. It rotates the reference phasor by an angle of 120 degrees, keeping the magnitude same. Keeping the magnitude same. So whatever you multiply it by a 1, it will always remain same. That means why we are having kept the alpha operator magnitude 1, because whatever has been multiplied with that vector, it will keep the it will keep the vector with the same magnitude. It will not change. But yes, it will change its phase. It will change its phase angle by a 120 degree. Is this clear? Now look at this. Now this is the sequence network for the transformers. Similarly, as we have discussed in the transmission lines, this is the sequence networks for the transformers. The positive sequence, negative sequence, and zero sequence network for the transformers. The positive and negative sequence networks for the transformers are quite similar, looks quite similar with the comparative to the transmission lines, but for the zero sequence network, it is completely changed. It depends on the configuration of the transformer. That means whether the transformers are connected in star connection, delta connection, or what at the primary and secondary sides. Okay, star grounded or star ungrounded. Okay, all these such type of things. Equals to. That means if a single line to ground fault, that is an LG fault, occur on a three-phase isolated neutral system, then how the potentials of the healthy phases will be equal to? It will be equal to √3 volts. It will be equal to √3 volts. We have seen that how we have calculated. For a three-phase system, when we are converting it into the neutral voltages, then it gives me the solution this one. Now, second question: if all the sequence voltages at the fault point in the power system are equal, then the fault is a. We know that the fault sequence voltages, the fault in point are equal, then the fault is what type of? It is a double line to ground fault. We will discuss this again in the unsymmetrical faults as well. Now, zero sequence current of the generator of a line to ground fault is 0 J2.4 per unit. Then the current through the neutral during the fault would be calculated. Calculate it, and I am giving you 2 minutes for this. Calculate the solution. It's very easy. The option is J 7.2 per unit. How it is coming? The line to ground fault current is the zero sequence current is given for an LG fault, and a neutral fault during the current has been given has been asked. Now obviously it is 3 times of it. It is 3 times the IA naught. So the IA naught is given, the fault current is been asked, then fault current will be equal to 3 IA naught. That means when we multiply the 24 into 3, it will be giving me the 7.2 per unit. Now the severity of the line to ground fault and the 3-phase fault at the terminal of an unloaded synchronous generator is to be assumed if the terminal voltage is 1 per unit and Z1, Z2 are 0.1 per unit and Z0 is 0.02 per unit, 0.5 per unit for the alternator, then the required inductive reactance for the neutral grounding is to be calculated. A 3-phase fault or symmetrical fault is occurred. The line to ground and a 3-phase fault at the terminals of an unloaded synchronous generator. It is important. So if the terminal voltage is given, Vt is given to you, Z1, Z2 and Z0 are given to you, then how you will be calculated? It will be nothing but Vt upon Z1 plus Z2 plus Z0. Okay, so Vt is given how much? 1 per unit upon Z1 plus Z2 plus Z0. It will be giving me 0.0166 per unit. Now the most frequently occurring fault in the power system is what? It is the line to ground fault. Why? In the distribution systems only the maximum fault are occurring. The transmissions are mostly protected, the generators are mostly protected, but the disturbances and the anomalies are coming only in the distribution systems. That's why the line to ground faults are more prominent in the frequency of occurrence. Now, which type of fault of the 3-phase components IA0, IA1 and IA2 are equal to IA0? That is, IA0, IA1 and IA2 are equal. That means they are in series. In which of the systems they are in series? They are in line to ground fault. Now, when the line to ground fault occurs, the current is in a faulted phase is 100 ampere. The fault current is given 100 ampere. The zero sequence current in this case would be, it will be double line to ground fault. Now, in which type of fault the positive sequence and negative sequence voltages are equal? That is, the VA1 and VA2 are equal. They are equal in the double line to ground fault because they are connected in parallel. The positive and negative sequence components are connected in sequence circuits are connected in parallel double line to ground faults. That's why their voltages are also equal. The fault analysis in power system symmetrical components are used because they give a sequence network do not have mutual couplings. And the last question, choose the correct one among the from the statement given. There is a minimum sequence voltage and maximum negative sequence voltages at the fault point. No, it is not right. Why? It is saying that there is a minimum sequence voltage and maximum negative sequence voltages at a fault point. You cannot say that a negative sequence voltages are always the maximum. No. Second thing is that look at option C. Zero sequence and negative sequence voltages are minimum at a fault point and increases towards the neutral. No, it is also wrong. It doesn't increases towards the neutral. And the none of the not, the option left is out, is option B, that is a zero and the negative sequence voltages are maximum at fault point towards the